Okay, our second talk, titled Capacity Estimate for TRO Channels, it will be given by Li Guo. Let's welcome the speakers.
Hello. Thank Michelle, thank the organizer for giving me this opportunity to talk. My topic is about some capacity estimates, and we are from a more mathematical point of view. And I will make it clear this notion TRO channel in my talk. This is a joint work with my advisor, Miles Younger, and Nicolas Lara Quinter. Okay. So a quantum channel is a completely positive trace preserving map which sends quantum states from Alice to quantum state to Bob. And it admits this Stinespring dilation, which is given by an isometry V from Alice to Bob and environments. And the channel can be represented by a partial trace of E composed with the conjugation of this isometry V. Then the complementary channel is instead of tracing out the environment system, we trace out the Bob system, look at what's the synchro sent to the environments. The quantum capacity asks the following question: how many qubits per use of channel can one send over it? And this is related to the information measured, the coherent information, which is the largest entropy difference between Bob and the environments. And the quantum capacity, thanks to the Lloyd-Schur-Devatak theory, is given by a limit of the average of coherent information over many uses of the channel. It is known that there exists a quantum channel such that the coherent information of a channel is strictly less than its quantum capacity. Hence, the limits, the so-called regularization, is necessary to see the real capacity of a quantum channel, but this makes the formula hard to compute. For example, we have this qubit depolarizing channel which sends qubits faithfully with 1 minus lambda probability, but with the rest of the probability is just output some random garbage. And in that case, for this kind of channel, the capacity in general is open, it's not known. There are some good cases. A channel is called a degradable channel if we can write its complementary channel by a composition of another channel with the original channel N. And by Devatak and Schur, the channel is degradable, then we know their coherent information equals to their quantum capacity, hence, and then the regularization is trivial in this case. An important class of degradable channels are this Hadamard channel given in the form like this. And here the ij is the computational basis, and the family of vector hi satisfies certain conditions to make this map trace preserving. Then it's natural to ask the question, are there other channels has the same property, the coherent information equals to the quantum capacity, so the regularization is actually not necessary? On the other hand, it's also good to have some upper estimate on the quantum capacity. There are many work done in this direction. Here I just list a few of them. Briefly, Smith, Smalling, Winter, they introduced this quantum capacity assisted with a symmetric side channel. A symmetric side channel has 0 quantum capacity, but if a channel assisted with that may increase its quantum capacity, hence its upper bounds. And they use these to give a previous best known bound for this qubit depolarizing channel, and this bound is improved by Suta and his co-authors use the idea of approximate degradable channel, and that is to consider a channel smallest distance to a degradable channel and use this arrow distance to give estimates. And also there is a semi-definite programming upper bound by Wang and Duan. And today I will present a new approach by doing analysis about this Stinespring dilation. So the plan of the talk is as follows. I'd like to first illustrate our main result by 2 examples. And then I will formally introduce these TRO channels and their modifications. And our main technical result is inequality about this so-called sandwich Ryan-P divergence, which I will define later. And we call this a comparison theory because it really compares these information measures between different channels. Okay, so let's look at the first example. Consider G is a finite group, and we can have an orthonormal basis indexed by the group elements of G, and denotes this lambda G to be the shift unitary by the left matrix multiplication. Then for each probability distribution F on this group G, we can define these random unitary channels according to this probability distribution. And we have an estimate for this kind of channels quantum capacity, that is the quantum capacity of the channel with probability distribution F is lower bounded by a maximum of 2 parts. One part is the logarithm of the size of G minus the entropy of F. Here F is here the entropy is actually a Shannon entropy. And also the second part is the quantum capacity of the channel with the uniform distribution. Here we denote it by N1. The upper bound, however, is the sum of these 2. So this is estimates with upper and lower bound differ at most to a factor of 2. So this channel is not degradable if G is not commutative. If G is commutative, this channel is actually can be written as a Hadamard channel. And for example, if you take the G is the group of 2 elements, then you recover the bit flip channel or equivalently the qubit dephasing channel. And the quantum capacity of this uniform distribution 1 is actually equals to an interesting number. Is the logarithm of the largest degree of G's irreducible representation. For irreducible representation, I mean a representation of those unitaries by the matrix, but we are not allowed to take a common diagonal, block diagonal structure. And the quantum capacity is just the largest size of this kind of irreducible representation. And it is a measure of non-commutativity of the G. In the sense, if G is commutative, this quantity is 0. If G is not commutative, it has to be strictly positive. So that's actually is a prototype of our estimates. We will consider a class of channels with one special one has the smallest capacity, and we consider all the other channels' capacity compared to that one with this correction term related to the entropy of F. Okay. The second example is more explicit. We consider this 4 to 3 dimensional example. It will trace out the first 2 by 2 block, just sent to its trace, and it will deface the right down corner 2 by 2 block, and then it select the matrix entry 1, 3, 2, 4, and 3, 1, 4, 2, and add a defacing factor alpha. Alpha is a parameter between -1 and 1. For this channel, our upper bounds is actually achievable here and actually equals to the coherent information by this following formula. 1 minus the binary entropy function, 1 plus alpha over 2. So again, this channel is not degradable since the first 2 by 2 block goes to the environments and the bulb has no way to recover it. As I mentioned, our approach is to understand the Stinespring dilations. Then we introduce this notion of Stinespring space as the image of the isometry, dilation isometry. And this image sits in the tensor product Hilbert space of bulb and the environments. It's immediate to see that this space, as a Hilbert space, is nothing but the input space, but its relative position in this tensor product space actually encodes all the information about this channel. To see that, we just need to use the identification. We identify this tensor product Hilbert space to operators from environment to Bob. By using that, you can rewrite the channel on the rank 1 inputs, basically by matrix multiplication. And the same thing for the complementary channel, but you reverse the order. So then it's natural to expect one can extract some information about the quantum capacity based on its Stinespring space, or at least based on some good Stinespring space. To have some warm-up examples, let's consider the trivial channel on the n-dimension space. Since everything now goes to Bob and environment system is trivial, you will have a column vector space. The row is just 1. Then in the opposite, if we consider complete trivial channel, a trace, then since Bob now has a trivial system, so the Stinespring space will become a row vector. If we consider tensor product of these two, then you will have a partial trace. In that case, the Stinespring space will be a tensor product of a column vector and to a row vector, which will give you a rectangle matrices. As further consider this direct sum of partial traces, it will drop off all the off-diagonal block and play the partial traces on the diagonal blocks. In that case, this Stinespring space will just be an orthogonal sum of rectangle matrices with different size. And this is actually corresponding to this kind of channel corresponding to the condition expectations from a non-commutative probability point of view. And by Fukuda and Wolf, we know the quantum capacity of this kind of channel is clear. The best strategy is just to use the largest error-free input system. So actually, you don't need to do the decoding as you cleverly choose the input space. Sorry. This kind of Stinespring space actually corresponds to this notion, Ternary ring of operator, finite dimensionally. And algebraically, this concept is defined almost 40 years ago by Hastings. Formally, a Ternary ring of operator is a closed subspace of a bounded operator from one Hilbert space to the other, such that it's closed under this Ternary ring action, which is a triple product x, y, dagger, z. It's immediate to see all the rectangle matrices and their direct sum satisfy this condition because that's the right way to do the matrix multiplication according to the size. It turned out to be all the finite dimensional TRO or Ternary ring of operator are exactly a direct sum of rectangle matrices with some additional multiplicity. But since here the multiplicity will not affect our capacity, so we will just call a channel a TRO channel. If its Stinespring space is a TRO, so we know it's we know by previous example they correspond to this kind of orthogonal sum of partial traces. Of course, these are restrictive examples, but they have clear capacity as we have seen. Further, we do some perturbations for these maybe trivial, almost trivial channels. The idea is also simple. We do a matrix multiplication after the identification of the isometry V. And since we want to have a quantum channel, so it's natural to consider when this matrix multiplication gives us isometry in the Hilbert-Smith norm sense. To answer that, we borrow the concept from non-commutative probability, the independence. So recall a normalized trace is just a trace divided by the dimension of the matrix, and a positive element is a normalized density if it has this normalized trace tau equals to 1. And then the independence of two algebra really means if you consider this normalized trace on a product of two elements, one from each algebra, it equals to this product of two normalized trays. And further, you can say an element is independent to an algebra A if the algebra generated by these elements, which is the closure of the polynomial of the elements and its dagger, is independent of the algebra A. With that, we can give an answer to the question as follows. When the square of A, the F, is elements in the environment system, is a normalized density independent to the range of the complementary channel. To make this setup more clear, we can say we start with the TRO channel written in this matrix multiplication form and choose a normalized density independent of the range of complementary channel. Then the map of defined on this rank 1 inputs by this triple matrix multiplication, just A inserted with the F Y dagger, is again a channel. It is completely positive because F is positive. It is trace preserving because of the independence. Then this really means some orthogonality condition. Basically, the F minus the tau of F, the traceless part of F, is an orthogonal element to the linear subspace of range of the complementary channel. It is immediate to see if you use the identity as the parameter F, then you recover this TRO channel. And for every F, this channel is better than the original channel. In the sense, you can write it as a lifting of the TRO channel by this conditional expectation, which is basically a projection from the entire bulb system onto the range of the N. Then our main technical result is an inequality about this sandwich rank EP divergence, which I give the definition here. And with the above construction, we can control for every single input row and every positive elements inside the range of the TRO channel, such that they are rank EP divergence of the output of rho and with respect to sigma is lower bounded by the same thing for the original TRO channel, upper bounded with this additional correction term. And this correction term is something also is a rank EP related to this rank EP entropy of the F, parameter F. Let me recall some basic property about this sandwich rank EP divergence, which we will use. So first, if you take the limits of this parameter P goes to 1, then it's recover the usual divergence, also called relative entropy. And it satisfies this data processing inequality, which will also be used later. For our purpose, we're interested in this coherent information of a channel. And we use the way to write it as a negative conditional entropy, then further can be expressed by this also relative entropy. That's actually give us a path to reach this capacity estimate based on our rank EP information measure inequalities. And then the result is that the quantum capacity of the channel with parameter F is greater than the quantum capacity of the original TRO channel, and that's the net plus a correction term tau F log F. In particular, we know this TRO channel, they are just the orthogonal sum of partial traces, so they have clear quantum capacity by the logarithm of largest error-free system. So the proof is, as we mentioned, we just first apply, if we assume our technical result, we first apply it to the amplification of channel, identity tensor channel. And then we have the inequality about this rank EP divergence. You take the limit P goes to 1, you have the relative entropy inequality. If you choose the right sigma, Then you can have the coherent information inequality. Then you take the supreme of all bipart input row AA prime. Then you have the coherent information of channel satisfy the analog of our estimates. The regularization is handleable here because our setup is stable with this tensor product. Basically, if you choose a k use of this channel with parameter f, it can be written as the original channel to the k copy with modified by this parameter f tensor k power. And this correction constant term is linear to this tensor power. So I will just briefly say a few words about the technical series proof. As the lower bounds is easy, it just follows from data processing inequality by this nice lifting property. While the upper bounds, we use complex interpolation. Here, this is only a sketch, it's an informal outline of the proof. The idea is to consider, the idea is we use this right multiplication to modify the Stinespring space. So we want to track how the Shelton P norm is changed on this multiplication. And the complex interpolation gives us a way, if we can control the P equals to infinity, the operator norm, and we can control the P equals to 2, the Hilbert's mission norm. We can control all the Shelton P norm between 2 and infinity. And these two boundary cases, they are true. One is because this multiplicative property is true in general. The other one is for the Hilbert's mission one is by our assumption on the independence. Then we have the Shelton 2P norm inequality. Then you just need to choose the right inputs, right thing to plug in, and square that inequality. You will have finally the thing we want in the norm form. And you just take a logarithm and multiply the right scalar. You get the technical inequality. Two remarks on our capacity bounds. First, this term tau f log f is actually really related to the entropy of f. It equals the logarithm of the size of the environments minus the entropy of f. But now f is not a density in the usual sense, so we add this normalization constant. And more interesting, our technical result has this local property. It's an inequality works for every single input. So it's natural to observe if you restrict your channel to any sub-input system, then this comparison of quantum capacity still holds. So that makes this setup more flexible. We prove something for exactly the TRO channel, but we can have the restriction also satisfy. So for some further applications, I want to talk about these following topics. First, there's a classical private capacity of a channel, which is also discussed in previous talk. Here, I just want to discuss the most basic without any assistance or two-way communication ones for simplicity. So it's given also by this regularization with this so-called private information of channel is the largest difference of two mutual information. Then it also known that there exists a channel such that private capacity is strictly greater than its private information. And in general, the quantum capacity is less than the private capacity because we can always use one entangled bit to generate one bit of secret key. Then for degradable channel, they are pretty much the same. This is a result by Smalling. So in our case, with all the previous setup, we will have the same comparison result for the private capacity. And we know for this kind of TRO channel N, the private capacity will be the same with the quantum capacity because it's just the largest error-free system. So we find our bounds for the quantum capacity works for this case, works for the private capacity. But I single out this red part because this red part also works for any restrictions of this class of channel. Another thing is this potential capacity introduced by Winter and Young to consider the superadditivity phenomena of these one-shot expressions. Basically, you take the superrim of the capacity, the coherent information of the tensor product of two channels and subtract the coherent information of the assistant channel. So a channel is called strongly additive for a one-shot expression if the potential capacity equals to the one-shot capacity. And we know for Hadamard channel, actually proved just in this paper, they show for Hadamard channel they are strongly additive both for both for the privates and the quantum communication. And in the case here, we have the similar comparison for the even combined the potential capacity. Again, the red part works for all the restriction. We can restrict channel to a subsystem. The black part in this formula is because the N channel is this special direct sum partial traces. Finally, I will use the result in the last talk by Wilde, Tomamiho, and Belta. That's the relative entropy of entanglements is the upper bound for the smallest strong converse rates for the private communication. And we see the relative entropy of entanglements is a definition based on this divergence. So our RAN-EP divergence inequality applies here to give upper bounds, similar upper bounds for the relative entropy of divergence. Relative entropy of entanglements. And then in the standard case with the TRO channel, we can get upper bounds also is a strong converse rate. Many concepts, but let me cook up all the things in this final interesting example. Consider rho is a 16 by 16 dimensional matrix. Then we write it in the form by the 4 by 4 matrix blocks. Then we define this channel by outputs a trace of each block tensor with some other 4 by 4 matrices and output as this corresponding JK matrix entry. Then with the F given by this form and X, Y, Z are Pauli matrices with some parameter alphas. Then we observe for this kind of channel, they have a clear formula for the quantum capacity and also private capacity. Moreover, we show the coherent information equals to the private information equals to the strong converse rates equals to the potential capacity given by this formula 1 minus the binary entropy 1 plus magnitude of alpha over 2. So here the magnitude of alpha has to be less than 1, which means this parameter f is actually a Borcher's field, is a qubits. Then we have the capacity equals to 1 minus the entropy of the qubits. So this shows this channel actually has a regularized capacity and strong converse and superadditivity, strong additivity. But it's not a degradable channel because if you look at this one, you plug in there, let's place a trace for these first 4 by 4 blocks and also for all the diagonal 4 by 4 blocks. So there's something goes to the environments, but the bulb cannot recover. So that's some new example we find. To sum up, I just want to mention we find the correspondence between this kind of TRO Stinespring space with the orthogonal sum of partial traces. Then we further build a perturbation theory for this orthogonal sum of partial traces channel and give capacity estimate on this modification by the matrix multiplication. then our estimate can be tied for certain example. In particular, we find the example with non-zero capacity, which is strong additive, has strong converse, have everything like, has nice behavior like a Hardy-Macher channel, but is not degradable. So for some future consideration, we'd like to see, to be honest, our estimates apply to this qubit depolarizing channel. A direct application does not give us a tight bounds, but we have this more flexible restriction setup. We have not explored it enough yet. So we hope by using that, we can say something interesting about the depolarizing channel. And I think that's all I want to say. Yeah. Thank you for the attention.
Okay, do you have any questions? So, let me ask one. So, do you think you can use this similar idea to construct example that you can show superactivity result?
Yes.
Because
yeah.
having a superactivity, like small case of superactivity result, a channel would be very interesting.
Well, as you see, our estimates in this TRO case actually bounds a lot of things. It may not be tied, but for certain example, it's tied and it shows like this final one. It shows strong additivity. It actually can tell us something with nice behavior. So it may not have the ability to tell us something there's a superadditivity violation. But I think that's an interesting question, because actually here, the lower bounds we find by some case-by-case study. We want to find the right subspace that this upper bound is achievable. But so far, we don't have an idea how to see a real violation of additivity.
Do we have any other questions? Okay, if not, just thanks the speaker again, and I will present the souvenir to him.
Thank you.